Lesson 3.1 covers scatter plots and linear correlations. So the answers to many questions are not as clear-cut as we sometimes think. We hear a lot about this in the media or in the newspaper, such as does smoking cause lung cancer? Is job performance related to high school marks? Okay, so two variable statistics, this is what we're getting into. They provide methods for detecting relationships between two variables and for developing mathematical models of these relationships. By visually representing our one variable statistics, like through graphing or like plotting points, we're better able to see the nature of the relationship between two variables. Okay, so here are a couple definitions just to start. We have dependent variable, and that is a variable that changes as a result of a change in another variable. So this one depends. Okay, and I know we've went through this before. Independent variable, this is the one that we actually control. This is the control variable. This one's along the x-axis, dependent variables along the y-axis. Okay, and an independent variable, this is the one that we manipulate to determine if there's a change in the dependent variable. When we talk about scatter plots, this is just a rough relationship. So for example, if you have an x and y axis, it can be one quadrant or four quadrants, it doesn't matter. It's just basically the points, and it shows the relationship. It represents the dependent variable along the y-axis and then the independent variable on the x-axis. It just represents the relationship between two variables by graphing it. And then when we have a scatter plot, we're able to use the line of best fit. This is a straight line. Of course, every line is actually straight, but for example, like this, a straight line that passes as close as possible to all of the points in the scatter plot and through as many points as possible. And this is basically what we're going to get into in this unit. The stronger the correlation, this means the more closely the data points cluster around the line of best fit. So take a look at these examples of a line of best fit. Let's actually classify the relationships between x and y. Okay, so for A, if we actually drew a line of best fit, which is just approximately like this, we can see that there is a strong positive correlation between whatever x is and whatever y is. So when we talk about positive, we mean that it's increasing to the right. Okay, and B, we can see that it's decreasing as we go to the right, we move to the right. This would be a strong negative correlation. Okay, and when we talk about strong, we talk about how closely these points are clustered around that line of best fit. So if you can take a look at A and B, they're almost perfect lines. Okay, C, these points to me are everywhere. Okay, they're in the top left, they're in the bottom left, top right, bottom right. I'm going to go ahead and say no correlation. So whatever happens with x, however you manipulate x, the y itself is just going to be everywhere. And D, we do see that it does go up to the right, but it's not as strong. So let's call this a moderate positive correlation. So again, positive means that it's going up to the right, and moderate means that the points are a little bit further. If we take a look at the actual distance between the points and the line, they're a little bit further from the line than A or B. E seems to be going up as well. We can either say moderate or weak positive correlation. And again, weak is just meaning, and we'll get more into the actual numerical definition, but weak just means that they're even further away from that like they're clustered further away from that line of best fit. And then F, we see it's negative. I would say either negative, strong, or moderate, because those are pretty close. All of these are pretty close. So let's say even moderate. Let's go moderate. Negative. And it's negative because, again, it's moving down to the right. Correlation.